Welcome to Study Loop.
So this question says there is a balloon of volume 750 meter cube and it has to be filled with hydrogen and kept at atmospheric pressure E1 is equal to 1.01 into 10 to the power 5 Pascal. Now how do we fill the hydrogen atom is the hydrogen atom are stored in cylinders and the cylinders each are of a volume 1.9 meter cube and the gauge pressure of uh, the cylinder that is seen on the gauge of the cylinder is 1.28 into 10 to the power 6 Pascal. Well, so since this is gauge pressure, I would not write it P2. I will just write it Pg, and P2 will be determined as, which implies P2 is equal to what? P2 is the sum of gauge pressure and atmospheric pressure. That gives us the actual pressure. So the actual pressure in the cylinder is 13.1 into 10 to the power 5 Pascal. Now the question says, how many cylinders are required to fill up these balloons? Now let n cylinders are required. Okay, so I suppose n cylinders are required. Then what are the number of moles required? N1 is equal to P1 V1 by RT. Since the temperature is same, so I just write RT. So what is the number of moles in each cylinder? N2 is P2 V2 by RT. Now since n cylinders, capital N cylinders, since capital N cylinders each having N2 moles of gas will fill N1 moles of gas. So what we can write is N1 should be capital N times N2. So if you equate these two, you get P1 V1 is equal to N times P2 V2 because RT get cancelled out. Therefore N is equal to P1 V1 upon P2 V2. Now just calculate this. We have P2, we have P1, we have P2, we have P1. So if you calculate this comes out to be 30.64 tanks. Well, these many tanks are required to fill up that one balloon. Okay, so let's move on to this is with part A of the question. Now let's move on to the next part, that is B. What is the total weight that can be supported by the balloon if both the gas in the balloon and surrounding air are at 15 degrees Celsius? So the weight that can be supported by balloon depends upon the force due to buoyancy. Suppose in addition to its weight, m mass is supported. In addition to its weight, okay, apart from its weight, m mass is supported. So how much weight does that balloon has to carry or apply the force, that is mg for that mass m, then its own weight, right? So its own weight is what? Mass of that balloon into g. Now mass of that balloon is what? Volume of that balloon into density of the gas inside the volume, that is hydrogen here, right? So density of hydrogen into G. Now this weight uh, to support this all weight for the balloon, the balloon should have some force applied upwards, right? So that force is the center of, sorry, the force due to buoyancy, and that force due to buoyancy is given by uh, the mass of air displaced into gravity. The mass of air displaced is equal to volume of air displaced into density into gravity. So volume of air displaced is the volume of balloon itself, and density of air is rho a. Now this gives me the mass of air displaced, and g is the gravity, right? So what we want to determine is mg. So mg is equal to v1g rho a minus rho h. Now the question has v1. The question, we know I love gravity g. Now we know the question says that the density of air, let me write that here, density of air is given as 1.23 kg per meter cube. So we don't know rho h. So how to determine rho h? To determine rho h, we again use the ideal gas equation formulation that gives rho h is equal to P1 mass of hydrogen upon RT, RT1, it is the same though. So if you substitute the value in here, 1.01 into 10 to the power 5, the mass of hydrogen is 2.02 to 10 to the power minus 3 upon 8.314 into the temperature is 15 degrees Celsius, right? So 288 Kelvin. So this comes out to be 0.0852 kg per meter cube, right? So we found out the density of hydrogen here. So just plug these values in here. So we have V1, we have V1, we know the value of G, we know the value of rho A, we know the value of rho H. So just plug these all values in here and you get your answer, which is 8414.28 Newton. So this is the weight the balloon can support, right? Let's move on to part C of the question. Now in C, the question asks us about the weight that could be supported if hydrogen was replaced by helium. Now if hydrogen is replaced by helium, then the changes comes out in rho h, right? So let us find here rho he. Again, rho he is equal to P1. Now it is, instead of mass mh, we have mhe, molecular mass of helium, upon RT1. Now if you substitute molecular mass of helium to be mhe to be, where mhe is equal to 4 grams per mole, so 4 into 10 to the power minus 3 kg per mole. So if you substitute this mhe here to find out the density of helium, rho he, then you get this to be 0.169 kg per meter cube. Other thing that you can do very easily is that The molecular weight of helium is almost double to that of hydrogen. So since you can see from this equation the density is directly proportional to molecular weight, so so the density will also be double for helium because the molecular weight is double. So double of 0.08 is 0.1617, right? 0.085 is 0.17, so there is net equal, so you can do that way as well. So we have already done this. Now for C part, the weight that can be supported is V1g times rho A minus rho He by using helium. So V1 is again 750, G is again 9.8, density of air is 1. It is 1.23. It is what doesn't look like 3 minus 0.169. So this gives me mg is equal to 7800 Newton. Well, using helium gas will reduce the weight that can be supported. Okay, then this is the solution for the given question. Thank you for watching this.